So class begins. So I hope first thing that everybody did their homework, because we're going to go very, very quickly. There's a lot of material. So yeah, let's start. So we have two parts of this, and we're going to take a break in the middle. So the first part is technical, where we're going to go over all the reasons why we build and how we build phono stages, what's important, what's not important, what kind of noise we have, and what kind of topologies designers use to build a decent phono stage, and why. There are reasons why you use certain circuit in a certain place and so on.
Can I ask a quick question real quick? Will the presentation notes that you have on the board be available to us later on, or do we need to take notes on them?
Actually, we're recording them.
Oh, perfect.
Okay. So I was thinking of recording with a camera, but it's too much. So we're just recording this. The voice will be recorded as well. So there will be someplace.
Thank you. Sorry to interrupt.
And if not, then I'll give you the presentation. That's the other way to do it. Okay, so this will be the first part, and it's a very intense 45 minutes. The second part, we're going to actually look inside a few units. Some of them we have here, and analyze what manufacturers are putting in those devices. Is it gold, or is it just a down-to-earth kind of a design? So we're starting with a record. So first thing is, what is a record? Okay, so it's grooves on vinyl. And as we can see, basically there are different kinds of grooves where, let's see, okay, can I get that? No, I don't get the mouse. So, okay, so basically we have grooves on vinyl. Now we have very fast changes. These are the high frequencies. And we have very lazy ones. That's a low frequency. Now think about this. There's basically a magnet moving and between coils, or a coil moving between magnets. Now, when you have the high frequency, it's very quick, right? It's a lot of fast movement. When you have the slow movement, the low frequency, very slow movement. Slow movement, less voltage. Very simple. Okay, so magnets moving fast induce a lot of voltage. Magnets moving slowly induce very low voltage. So the issue was, how do we get high level of low frequency, because it doesn't induce a lot of voltage? Okay, so the solution is, okay, you can increase the groove so there'll be a lot of movement. That's not acceptable, because then we don't have enough space. So the other solution is, of course, to change the gain. So we said, by definition, we will amplify the low frequency, the 50 hertz and below, a lot. And the 1 kilohertz, the mid band, is going to be amplified by whatever we specify for the amplifier. The 50 hertz and below will be amplified by 20 dB, like 10x more. And when we get to the very high frequencies, well, we know that they induce a lot of voltage. Well, we really want a lot lower gain. So we basically end up with 20 kilohertz being 20 dB down, or 10x down from the 1 kilohertz. So this is the famous RIAA curve. Now, there are different curves depending on the manufacturer at the time, but everybody settled on the RIAA, so we'll talk about that. But what you see here is basically the points where they drop, and the points where it gets straight, the gain, are specified in frequencies or microseconds. And those are the differences between the different curves. So if you have a Columbia record or an old 78, they may have a slightly different curve. You change the circuit. I mean, you can build a circuit that will work for that particular curve. So we'll see how those are implemented. Okay, it's not super sophisticated. It's very simple. And that was the idea at the time. When they came up with this curve, they said, how do we implement that? And remember, these were tube circuits. They don't want to put a lot of stuff in that phono preamp. So they came up with very simplistic low pass, high pass amplifier stages. they said, this is what we do. We put a low pass at the first frequency, first order. We put a high pass at this frequency, which is second order, first order also. So the slope becomes straight. And then we put another low pass here. All of them are first order, essentially. So very simplistic circuits. Okay. Next one is a magnetic cartridge. So we have basically, fortunately, well, maybe there's a laser here. No. So we have a magnetic cartridge. So we have a tip, we have a cantilever, and then we have something moving there, magnets in between coils or coils between magnets. So to represent that electrically, because electrical engineers like to have a model that will mimic the frequency response of this kind of a structure. We know the coils are very little. They don't have any resistance. They don't have any capacitance. They don't have a lot of inductance. They're very, very simplistic devices. However, the whole thing together has mass and moves slower than ideal. And this is represented in the diagram on the left side. So what we see over there is a current source. The CCS is a current source. So when the needle moves, it really generates current. Okay, that's the model. And that current goes through some induction, which is pretty high, because the frequency response, the mechanical frequency response, is different than what you measure with an electronic instrument. So that a 0.8 millihenry is a pretty big solenoid. Okay, if you look inside amplifiers, you'll see, or crossovers, you'll see this is a pretty big thing. It cannot exist inside a cartridge. So this is really the equivalent circuit that mimics, essentially, we're saying here that the recording velocity is represented by, the inertia of the armature is represented by that particular component. And the thing is, if we take this circuit and we put it in a circuit simulator, it will give us a frequency response that resembles what we expect from that particular cartridge. So from that, we're going to real world frequency response, and we're looking at the cartridge response. So this is a moving coil cartridge. The ideal for this moving coil, as you'll see, is the top line, which is if you load it with 80 ohm. So the purple line, and it still gives you some peak, okay? Because we have essentially, when you put circuits with capacitors and inductors like this, there's a capacitor here, there's an inductor there. These are resonant circuits. Okay, they have a frequency and we can calculate that frequency. So they resonate at that frequency. Of course, the designer is trying to change the cartridge in a way that these parameters fall outside the audio band. So we don't have a lot of impact on what we're hearing within the audio band. So as we see from the next slide, basically there is always a peak. The resonance is somewhere in there, and it's not negligible. I mean, it can be very close to 20 kilohertz. And that means that has a phase impact on what you're hearing in the upper treble. Okay? So this is part of the design of a cartridge. In this particular case, the 80 ohm gives us a little resonance here, a tiny peak. But if we're changing vastly from it, we can see that the curve, the response becomes less flat and the peak becomes much higher. So this is basically why you should always check the loading, especially with MC, which is very little loading. I mean, they recommend sometimes 50 ohm. You should try different ones if you have a variable one like the Stellar has. You should try different ones And probably the best thing to do is measure the response to see which one is the ideal for your particular cartridge. But if you don't know, stick to the manufacturer's recommendation. Don't go by gut feel, okay? And I've seen that 50 ohm to 100 ohm, major difference in sound. Ask Jim.
The representation of frequency response?
This is the frequency response, yes.
And each line there's 20 dB then.
This is log, yeah. Each line is 20 dB.
So you get a 20 dB difference with 10 ohms to 80 ohms, which would make sense.
Yeah, it will be a big difference. And not only that, the 10 ohm, I mean, there's a difference between this frequency, the mid band, and the bass and treble. There's a big
Nice
dip.
smile curve.
And yeah.
Yeah. Well, you won't smile when you listen to it.
Hey,
Corey, you expected basically the flat response, right? And you're getting a funny response.
What's the ohms? The ohms is what? The resistance of the entire cartridge?
The termination resistance, like
Of the cartridge.
of the cartridge. So your preamp basically has, especially MC preamps, will have different ohm termination.
Okay.
Okay, and you pick the one that's closest to. Unfortunately, some of them have the lowest is 50, and the cartridge requires 20. Or the lowest is 100, and the cartridge is 50. And I've seen that, and it's a big difference. So the way you fix it is you can probably manipulate it yourself in the cable. If you have a very high impedance, minimum impedance, you can add a parallel resistor in the connector. You can fix that to some extent, but it's a major effect on the curve. So everything that we said before, that, you know, you follow the RAAA and so on, that's for ideal. That's assuming that you know this equivalent circuit, and based on knowing that, you terminate it correctly, like with the correct 80 ohm in this case. And then you get sort of a flat response from the cartridge that with the RAAA curve becomes flat response on the output of the phono stage. Okay? If not, then all this goes to hell and you have a curve that is not what you wanted. Okay?
Where's that data from?
This is all data that is available on the internet. I just picked the best. Yeah, it gotta be, right? I mean, I think this one is the Australian guy. I forgot, but I usually put the name, you know, where I got it, but yeah, this one I didn't. But there are several places you'll find it, and I tried to pick one that's the easiest to explain, right? Yeah, I think that's it.
I can send an email.
Yeah, I know.
So now that we understand what we're dealing with, we have basically extremely low signals, and that's what we didn't say up front. So we have very low signals. Moving coil. Oh, okay, right here. So moving coil will give us 0.2 to 0.5 millivolts in the 1 kilohertz range. Remember the curve, okay? So you'll get less in different places in the band, and you get less when there's modulation, like music. So this is like the highest you can get, okay, or the nominal. With moving cartridge, with moving iron or moving magnet, you get higher levels. And there are some moving coils that somehow generate high levels. So the curve is the same because the recording is the same. And the behavior of the cartridge is very similar, regardless of the technology, because we're talking about magnetic field and coils. Okay, so it's very similar. The levels are different because the coil in the moving coil is much smaller than a coil in a moving magnet. That's all. So our problem is once we have a cartridge, either with high output or low output, now we need to amplify that to line level. Okay, line level 0.3 volts nominal. Peak, not peak to peak, 1 volt peak to peak. So if we are dealing with 0.2 millivolt to get all the way up to 300 millivolt, that's 6,000. a gain of 6,000. Okay, voltage gain. The 2.5 to 5 millivolt, a little less. Okay, by a factor of 10. So it'll be still a gain of 600 to 1,000. And that is the mid-band gain. Remember, the base is 10 times higher. So we're talking about amplifiers, an amplifier, the phono stage, that can amplify the nominal mid-band at 1,000x and the base 10,000 times. Okay, now those numbers sound big. However, transistors and tubes are very good at amplification. They can amplify a lot. So some manufacturers prefer to break the gain into smaller portions, so each stage has less gain and they have more stages. For other reasons too. Some manufacturers say, no, the minimum is the best. The less stages, the better. And each stage has a lot of gain. And there are issues with a lot of gain. How do you control it precisely? So essentially practical issues. So if you're building a one-off, you can always do it. You can measure, you can tweak. If you're building a production line, you got a problem. You need QA, you need quality assurance. You need to know that if the first stage was supposed to amplify 100 times, that it does amplify 100 times and not 80. Okay? And there are ways to do that. We'll talk about them later on. So we are at the device level. So we need amplifiers. Amplifiers use amplifying devices. So those devices, the common ones are the three ones that we all talk about: the bipolar transistor, the JFET, junction field effect transistor, and the old technology is the tube. And everybody's asking, well, why old technology? Well, we'll start with that. So the triode is the simplest tube, and it's actually the preferred tube for this kind of application. So we're looking here at 6DJ, a common high gain, high transconductance, but it's supposedly high gain. So what we see here is a plate voltage on this axis and the current on this axis, and these curves represent the grid voltage. So if you saw the intro clips, there's basically a cathode that emits a filament that heats up the cathode, emits electrons, and those electrons are being pulled towards the anode by the plate, essentially, by the plate voltage. So we're trying to pull them towards the positive, very high voltage. And that is true in a diode, pentode, or triode. That's always the case. So the plate voltage tries to pull those electrons, and the amplification is achieved by repelling them. How do we repel them? We put negative voltage on a grid that's between the plate and the cathode. Okay, so now the more negative, the more repulsion. So it's actually like a reverse effect of what we think about amplification. We're not amplifying, we're lowering the amplification. If you let it go without a grid, it will be the maximum current. It'll be basically here. Well, the highest voltage with this curve going, well, which curve? This curve. 0 volt. Yeah, going all the way down. It's not going to conduct that way. But essentially, the lower, the more positive grid voltage, a relative scale because it's all negative, and the higher plate voltage, the more current you're going to get. Okay, so now we have a phono stage or any audio amplifier. We are bringing that input sine wave, which is alternating voltages, right? It goes up and down. So that alternate voltage at any point in time, if we freeze it, it's some voltage on this chart. Let's say we ended up at 0.2 volts, and we're using a plate voltage of 100 volts. So we intersect those two, and we get something like 12 milliamp flowing in that tube. If we change it by 1 volt, we drop from here to there, a big change in current. Okay, so this particular tube, every volt of grid changes a lot of milliamps. That's called a high transconductance tube. The reason there's a huge change is because the grid is extremely close to the cathode. So the effect of the grid is much higher than the effect of the plate that's far away. We still need the plate. Without the plate, the high voltage, the electrons will never go that way. So they're trying to go that way. But when we put the grid very close to the cathode, we get a huge amplification like this. So essentially the change of current to the change of voltage, that's what the tube does. And that's what we call transconductance. So a tube is really a transconductance device. You put voltage on the grid, you change the current. How do you get voltage on the outside the tube? You put a resistor. Ohm's law, you multiply current times resistance, that's your voltage. Okay? Now, the thing to note in a triode, look at those curves. They're 1 volt difference between them. And they're almost parallel. And the distance between them is almost fixed. This is a very linear tube. Okay? Especially with the high swing, if you have a lot of voltage. Now, in Phono stages, especially when you design the input stage of the Phono stage, the signals are millivolts. They're minuscule. So really, there isn't a lot of deviation. However, the shape of this chart tells you that this is a very linear device. There's very little change in the transconductance. So if a sine wave is moving around the 2 volts to plus minus 5 millivolts around the 2 volts, the change in current for 1 millivolt change or 5 millivolt change is going to be linear. It's going to be 5 times more for the 5 millivolt versus the 1 millivolt. If the device is not linear, there may be changes in how much current it's conducting, and that has an effect. We will see. So ideally, for audio or any amplifier, well, most amplifiers, we're trying to retain the shape of the original signal. If the tube has curves this nice, with equal spacing, even spacing, it's a linear tube. It's going to give you very good amplification without distortion. We will show distortion later. So if the distortion, the inherent distortion of a triode, like a 6 DJ, is very low, we don't have to fix it. Okay, we can live without negative feedback that fixes distortion or a lot of things like that. And there's some sonic effect to every decision you make. So another thing that we're looking at the curve and saying, well, how do we know how to bias, where to put the tube where our signal is 5 millivolt? Okay, I mean, should we put it at 0 volt and let it swing? No, because it will swing to negative. There's no negative current. Okay, what we're doing is basically biasing a tube. So like Tony today biased the amplifier. You put the amplifier tubes at a particular point on the chart, either here or there, whatever. And the reason you do that is because you want to pick the place for the particular circuit where it's working the most efficiently or the most linear. And in this particular case, it's a phono preamp, very small signals. So we will pick a point on the chart here where we see that the curves are the most linear. That will be the ideal for us. So the signal, just 1 second, the input signal from the cartridge is going to swing around that point, not much. And it's going to be extremely linear, generate the minimum harmonics and distortion. We can measure that. And in the lab, John Crow will tell you, he'll put a device on it and see, okay, this is how much distortion. Change the conditions, say, okay, I don't want it here, I want it there. And see, well, is this a better point? And you find basically where it's ideal, okay, for your circuit. So this is the biasing concept. So when you talk about biasing a circuit, this is what you do. You determine, you fix the operating point. You say, I want to put so much voltage, so much current. Now, in some cases, you have limitations. The tube cannot take more than so many volts. Okay, you cannot exceed. Or the tube cannot take more than so many watts. So the voltage you put on the tube times current, if you move to a higher current point on the chart, puts out more power dissipation and more heat. And then your tube life goes down. And so it's a chain effect. This is part of the decision of the designer, how to pick the best point, operating point that is still reliable. Okay. Triode. So triode, we understand. Plate pulls the electrons, grid repels them, and the total effect gives you the amplification. Next thing, we'll go to a JFET. Why? Because a JFET is really a transconductance device. It's the same concept as a tube, that we put voltage on one terminal and it changes the current through the device. However, look at this curve. It's not the same as this curve. Okay? The first thing we notice is that the curve is flat in relation to the voltage, to the battery voltage, let's say. Mm-hmm. So there are no electrons in space that are pulled towards anything. Okay? This device works by changing a resistance somewhere, and that changes the current. Okay? So the physics of how it works is different, but the mode of operation is still, you put voltage on one terminal, you get current through the other two terminals. So the effect of the drain source voltage is very minimal, which is actually a good thing in amplifiers. You know, one less factor to worry about. And you get higher drain current as you move with the input signal. And the input signal, again, is negative. So we're repelling, we're limiting the current. However, unlike the triode, we see with 0.1, a different scale, but it's the same concept. 0.1 difference between the curves, big difference in current. Okay, I mean, there's a lot more amplification here, there than here. So if you're at 12 volts and your input signal moves from 0.4 to 0.3, you only gain like 2 milliamp, well, 1.5 milliamp. If you're at 0.2 and you move to 0.1, you gain 4 milliamps. Huge, huge difference. Okay, so when you're dealing with JFETs with high swing, like a lot of volts, you got really serious nonlinearity. Okay. Mm-hmm. Fortunately for us, we're at Phono stages, right? So we're setting it up here, and it will move very little. Still, the general shape of the curve tells you the natural behavior of the device. It's not a linear device like a triode. Okay, but if you set a JFET at a very high current point, like a high bias relative to the signal that is coming in, the changes are negligible, okay, and you get low distortion, more than a tube, but acceptable level. Okay, so setting the bias on a device that is nonlinear inherently is a big task. Okay, and you'll see basically some designs are going for low power, but usually they try to hit the point where the device power dissipation is, and that's the highest current that they'll run in that device. They'll get roughly the same, well, whatever amplification they get at that point, and hope that this is linear enough. Okay, now all those nonlinearities you can fix, okay, but there's a cost to everything. So Negative feedback is what everybody's talking about. So you say, well, if it generates harmonics, we'll bring them back, subtract, we distort the input signal, and we'll fix the output. Yeah, you can do that. There are consequences to that. So ideally, you want to start with a very low distortion device, move on. Fix it if you need at a minimum level. Okay, JFET. Now we're going to go to the fun device, which is a bipolar transistor. So everybody thinks that this is the first transistor. It's not. The MOSFET was actually the first transistor. This was the easiest to build. So in 1948, you could buy bipolar transistors, but you couldn't buy the one they knew, the MOSFET. So this is slightly different. So bipolar transistor is not taking voltage and giving you current. Okay, it's not modulating current with voltage. So it's a little bit more tricky. It basically has, the curves are current. So there's a change in the input current to the device. However, what we see in this particular device, 3904, pretty common transistor, that when you're moving 50 microamps, you're moving roughly linearly on the output current. So if I pick somewhere in this area to work, to bias the device, it's pretty linear. However, because it is using input current, you have more issues. You have to set up the operating point by setting up a current, not a voltage. Voltage is easy. You can go inject to the grid another supply with a high resistance. You're done. Okay, and people do that. With this device, you cannot do it. You need current. And once you put a circuit that gives it certain steady current, let's say it operates with 200 microamp, that's resistors from the supply. And those resistors are not negligible. And the input signal sees the same resistors. Okay, so you have a little bit more complications. I won't go into how to design with bipolar or how to design with any of them. I'm just mentioning the characteristics of the device. So you could, and people did, design good phono stages with bipolar transistors because they're extremely linear. However, they consume current, so they load the previous circuit. And if you are counting on resistance, capacitance in the path, you need to take that into consideration. The device itself, any of those devices, okay, it's a real life device. It's not what the spec says. If you read this chart, you think that's the device. No, it can move because of deviations in manufacturing. And you have to account for those. And in some cases, it will shift your frequency response. Okay, so bipolar transistors, because they conduct, well, they have more inherent internal resistances than the MOSFET. Resistance, we will see, is a noise, source of noise. So usually you don't see them in extremely low noise circuits. There are some bipolar transistors that are good in that sense. They were manufactured specifically for low noise, and they improved the resistances inside the device. Okay, very few. JFET, you can take any of them. Okay, it's low noise inherently. Okay, because it's the way they manufacture it. Tubes, you really have to look at the characteristics. The higher transconductance is usually the low noise, but there's obviously manufacturing effects, like if there's gas in the tube because of Chinese manufacture in a backyard. There are cases, right? So you have to look at the quality of the device itself. So these are the three major devices that we're dealing with. There are sub-devices. There's NFET and PFET, and there are MOSFETs and all sorts of other devices. They're all relevant, But for phono, low noise, we will deal with these three, and you'll find them in a lot of circuits. You'll find bipolar in ancient circuits from the 70s. And while they were supposed to be low noise, the results are lukewarm. I mean, I've tried a few. So, distortion. Okay, so this is harmonic distortion. Basically, what we're saying is we're putting a 1 kilohertz signal into the input signal, and this is the output signal. Okay, but we put in only 1 kilohertz, pure sine wave 1 kilohertz. On the output, instead of seeing only the 1 kilohertz, now we see 2 kilohertz and 3 kilohertz, and you'll see 4, 5, and so on. So an amplifier is not ideal because it's not linear. Like we looked at those curves, we saw that it's not linear. It generates other things because the waveform on the output is not a sine wave. It's something else. Okay, so I'll demonstrate here the second harmonic. Okay, so we looked at the tubes of the curves of, well, any of them, the JFET, let's say, and we saw that in the lower voltages it has higher gain, lower gain than the higher voltages. So if we put a small signal in, and let's say this is double a 2x gain, this is the signal we expect. We expect the black signal there. Instead, because at the higher voltages it got more gain, well, we get the red thing. And at the lower voltages, it's actually less than the ideal, right? So we ended up with a distorted signal. We wanted a sine wave, we got an egg shape, whatever. Now, we take what we have on the output, the red, and we subtract the ideal, which is basically what we looked at the previous slide. So this is the 1 kilohertz. This is the ideal. The 1 kilohertz would have been the black sine wave on the output. And because we didn't get that, we got other things. And those other things are generated from the difference between the real output, the red, and the black. So if we look at that, we subtract it, red minus black, we get a positive peak here. And the funny thing is that on the reverse side, we also get a positive peak, not a negative, right? Because it's lower gain there. So it's actually above the ideal curve. And guess what? From a single peak, we got 2 peaks. Second harmonic. Okay? Very easy to see. So if you have a circuit that has a single, and most single-ended circuits with nonlinear devices will show a second harmonic. This is the reason, because the nonlinearity creates this kind of distortion. Okay? The fixes to that is like everybody will tell you, well, use a complementary circuit. One device amplifies more when it goes up, the other device amplifies more when the signal goes down. Eventually, you compensate for it. Yes, that will eliminate second harmonic, and that's a push-pull circuit in tubes or a complementary circuit for transistors. However, 2 devices are not one. Okay, you have to make the 2 of them work together. The curves of one have to match the curves of the other. Well, what if they're not coming from the same batch, the same manufacturer? There are so many issues with that. So then we're saying, well, we'll fix them in a different way. Again, we'll put some negative feedback. It will take all the crap, bring it back, subtract, and we'll correct for it. So that's one way of doing it. The question is that the ideal way of doing it? Well, could be. But as long as we're dealing with low-level signals, probably not necessary. Single-ended circuits are fine. However, you will see, and we'll look at some of those circuits that are a little bit more complicated. They use complementary circuits in low-level signals to compensate for harmonics in the first place. Okay, it's a choice. John Curl did that. Okay, his Vendetta does exactly that. It's a complementary circuit. Okay, let's get out of this one. So we dealt with the harmonic distortion. 1 kilohertz gives us 2, 3 multiples. Okay, there's also music is multiple signals coming together into the amplifier, not one tone. So if you have 2 tones, in this case, 19 and 20 kilohertz, it's just an example. I know why they did that. They borrowed from radio, but which was wrong. But anyway, it could be 3 and 4 kilohertz. Okay, still musical content, right? Those signals mix because of this nonlinearity. The levels between the two of them, when they sit on top of each other, change. You get some funny voltage swing, and that funny thing comes out distorted on the output, and the distortion is nonlinear. So when you do that with several tones, you end up with combinations of those tones. Okay, so you get first plus second. Well, first plus second is going to be in the 30 kilohertz. We don't care about that. But first minus second is 1 kilohertz in this case. And we do see a strong 1 kilohertz. We see a second harmonic of both of them mixing. And the higher harmonic are lesser level. Okay, but we do see a content of intermodulation like that. This is intermodulation. 2 tones coming in, they generate the plus and minus of those tones. Why are we differentiating between those and the harmonic? Because harmonic tones, in general, are real life kind of phenomena. Like you speak, you vibrate the wall comes back with 1 kilohertz, 2 kilohertz, 3 kilohertz because it vibrates. It's non-linear. Okay, so we're used to that. Your musical instrument generates harmonics. Okay, the string moving. It doesn't generate fundamental only. It generates harmonics usually, and it's sort of natural to hear harmonics. And that's part of the content of the music that we're listening to. Intermodulation is not that. It's things that were not in the original music. Now, some of it is created in real life when you have multiple harmonics hitting something coming back, but it's very, very low level. So the ear is a lot more intolerant to intermodulation distortion. Okay, and designers are really trying to cut that down as much as possible. How do you fix either one of those distortions? By making the circuit a lot more linear, or by fixing the distortion with some negative feedback. But a phono designer, because it's low levels, will try and up the bias as much as possible, try and get to an operating point where you have the least distortion, and then fix if you need to. Okay, sometimes you don't need to. Sometimes it's an acceptable level of distortion, and the fix for it has side effects that you can hear. Okay, and we'll maybe talk about it very quickly. Okay, I'm running very late here. We're at 13 out of, I need to cover 30, and time is gone. So we'll go very quickly over this. So equivalent circuit of an amplifying device, either a tube or a transistor. So we have basically an input. Went to the wrong. Yeah, that's an equivalent circuit. So basically we have input voltage coming from the previous, and we have an output. Now remember, we said we have input voltage times the transconductance of the device. We get an output. The voltage develops over the internal plate resistance or whatever internal resistance of the device plus the load. Okay, so the load basically takes some of the current that's generated in the device and gives us the output. Okay, but remember, it's not only the load, there's actually an internal resistance which is specified by the manufacturer. So we need to take that into consideration. And if you simulate, you'll see it. If you build a thing and you say, why the tube doesn't give me what I thought it will? It says a mu of 100, why am I getting only 50? Because it has internal consumption of that output voltage. Okay, so let's look at real circuits. So this is a tube. We have a power supply. And I think you looked at some of those circuits. So the tube basically is set up with 0 volts here. And we don't want 0 volts on the grid, right? I mean, if we connect the grid to the reference 0, this is the ground, what we call ground. It's a 0 volts for us. If we connect it to 0, we're at the low end of the curve. If you remember, we'll go there. There you go. I mean, we don't want to be here, right? We want it to be -2 volts, maybe -3 volts. So how do we do that? Well, this particular circuit is very simple and clever in a sense. It says basically there will be some current going on. The current will flow here. The voltage that it drops on this resistor is negative grid voltage. Why? Because from here to there, the current flows downward. There's a positive voltage here. Let's say if it's 2 volt positive, the cathode is at 2 volts. This is at 0 volts. Well, guess what? It's in the negative 2 volts versus the cathode, the grid. Okay, so there's no fixed voltage. Okay, everything is relative, and voltage is potential, one potential versus another. So as long as we have a cathode at a higher voltage, positive voltage than the grid, we're in a negative grid voltage. We're on the curve, okay, at a bias of -2 volts. The current is developed, signal comes here. The current is developed in this circuit. It falls on this RA, the load, and on this load as well. So from a from a voltage point of view, both of these loads are seen by the tube. The current splits between them. The tube itself has the internal resistance. The overall effect of that is still higher voltage on the output than voltage on the input. Okay? And the trick was to find the good bias point with what the right current and everything that gives us the lowest noise possible. Now, when you look at circuits, you'll see a capacitor. A lot of people will put a capacitor right next to the amplifying device or stage. And you think that this is just to retain current from the power supply. It's not. Okay? This is, and people bullshit about the signal path capacitors versus supply bypass capacitors. This is a signal path capacitor. Okay? It looks like a supply capacitor because it does function to hold current or charge for the tube. So the supply doesn't sag. Okay, when the tube conducts more or less current. But it also puts the B plus rail at the same potential from a AC, from a audio signal point of view. The capacitor is conducting. It's not DC. And we want this capacitor to conduct at a very high rate all audio signals. Why? Because we want the rail, the B plus rail, from the AC point of view to look like ground. Okay, it needs to be a ground potential. This is part of the audio circuit. This is not just DC. And if anybody will tell you you can put electrolytic and not worry about it, don't. You need to bypass this electrolytic if you want to get decent results, because The electrolytic will be fine for DC, not for AC. And you need the AC behavior of the circuit. This is a similar circuit, very similar effect. The JFET, it drops voltage here, so you get negative voltage over there. Okay, and this is for NFETs only. PFET is the opposite. You want a positive voltage, but we're not going to talk about the details. I mean, this is way more complicated. This is the bipolar transistor. Well, we said a bipolar transistor is a current amplifying device. So we have to set up the operating point, not by voltage on a grid, but current through the base. Well, to put current through the base, we need a divider here that sets up the voltage. At this point, there's some DC voltage. It drops to this point, 0.7 volts, which is a diode. I'm waving hands a lot. And then this determines the current here. So this is how we set up the bias, the operating point of a bipolar device. A lot more complicated than the circuits we saw before. The circuits before just had a resistor essentially loading the previous stage. And go back. Yeah, loading the previous stage. And this resistor is pretty high. So it's not really loading the previous stage. So it's very easy to design. With bipolar, you're dealing with low resistors. There's real current flowing here. So you're loading the previous stage, and those resistors are not negligible. They have noise and so on. So there's a reason why people use less and less bipolar in current, in at least preamp in Phono stages.
The Sutherland Loco is, I think, a current Phono stage. Do they do bipolar?
I don't know the particular one. From what I've seen, Sutherland, op amps everywhere. Okay, we'll have an example. Well, we'll have to go through the examples very quickly because there isn't much. All right, this is what everybody hates. So there's a feedback amplifier. It could be an op amp, like this A could be an op amp. And what we're seeing here, there's a little bit of funny math. Basically, we're saying, well, we'll take the output, multiply it by a small fraction, a fraction of the output, bring it back here and subtract. So Vx becomes basically the input minus the portion of the output that's subtracted. Okay, why are we doing that? Because if there's distortion on the output, we can bring it to the input, subtract it. Okay, and then go back through the amplifier, and it will try and eliminate the differences. That's the idea, especially if the gain A is extremely high. So that's what op amps are doing really well. They build multiple stages with a gain of 1 million. Okay, nobody wants a gain of 1 million. Okay, so we cut it down with the feedback to a gain of 20. All right, that difference is used to basically fix the waveform on the output. Okay, so the level of negative feedback is essentially the difference between the potential gain, like 1 million, and the actual gain, 20. So the difference is 5,000 or 50,000. You take a logarithm of that times 10 times 20, and that will be the level of negative feedback. So you can see that op amps start with a lot of gain and end up with a circuit with relatively low gain. So the negative feedback level is huge. Okay, we're reducing the original gain a lot. When you do that, you have a few issues. First, you have inside the op amp several stages. And you should ask yourself, do I need that many stages? Because each one of them contributes nonlinearity by itself. And then you have with more stages, you have delays. Every device is not instantaneous. Okay, so you bring the signal back. With those formulas here, they say, well, you know, the signal coming back with no delay, essentially, right? Because we're saying Vx is Vi minus beta Vo. No, it is minus beta Vo. However, Vo is not Vi times A, like in the next formula. It's really delayed input signal times A. Okay, you bring it with some delay, now you have a phase differential. Okay, those create their own sound, their own distortions. And it's not negligible unless the original circuit, the main amplifier, is a very fast amplifier. Okay, now in phono stages, we want low pass and high pass to have the RAAA response. Well, guess what? Low pass and high pass involve capacitors. You delay the signal, whether you want it or not. Okay, so all those amplifiers are feedback amplifiers. If they are feedback amplifiers, they're dealing with delayed outputs. Not ideal. Okay, so this is my issue. Anytime anybody talks about feedback as the magic solution, it's not a magic solution. If used with care, you can get good results. If used just for the fun, you know, let's fix it because the theory says it's good, you end up with something that's not great. I think for me, the main thing I see with designs that use a lot of negative feedback just to fix problems like distortion is they lose the natural attack and decay. You just don't see this, feel the speed of signals. Some of them are good. Some of them are very good, and they're very careful where they apply the negative feedback. Some of them are not. So don't use feedback as a magic solution. Think about it. No free lunch. Has consequences. So this is just to demonstrate op amps. So an op amp is basically a device that has a lot of amplification stages, and some other time we'll talk about it more in detail. But I wanted to show basically, so this is a discrete op amp, which follows very much the little op amps you buy, the 8-pin op amps you can buy for 50 cents. Okay, so it's the same circuit, except for in the 70s or 80s, Dean Jensen from Jensen Transformer said, you know, recording studios are using those op amps. We don't like the sound because they didn't understand the negative feedback. They thought it's the circuit itself. He said, I'm going to build discrete op amps because I can control every device I pick and you get better performance. And he did get better performance. Not only that, he used inductors, which you cannot put in a small silicon chip. Okay, so this is a very, very good op amp. So the 990 is like the holy grail of recording studios from that time. I want to show you the evolution of that. So Balder basically bought the 990 and built their first amplifiers with the Dean Jensen amplifier modules. And then they decided, you know, we need feedback. And they needed DC feedback. It didn't do what they want. So they designed their version, the 990 DC, which is very similar to the 990, the Dean Jensen, but better performance at DC, so they can do DC server with that. And then they improved several generations, ended up with the 993, which is essentially, topology is still this. It's still the 990 Dean Jensen. You can buy it today from a few companies make similar devices, around $70 if you want to build a similar device. I assume that Boulder pays a little bit more attention to the quality of what they put inside those modules, but you're pretty close if you're buying one of those modules, and a lot of studio equipment will use them, like high quality. Other types of op amps you can see in the circuits sometimes, and we'll see later on.
Or just quick question.
Yes.
Is this in parallel? Is this another way of doing a tube feedback?
Yeah, essentially.
Okay, so it's just
It's
replacing
an amplifying device.
or a JFET. Just
Or
another
JFET,
version.
yeah.
Okay.
So the thing is, this is using transistors or JFETs. It can make several tubes. The idea is basically to have a lot of gain, so you can do a feedback amplifier, right? So this, to have this work well, you need the gain to be very high. Okay, and if the gain is very high, the whole math shows you that the output of this circuit is independent of that high gain. It's really determined by how you construct your feedback. Okay, if you have low gain in A, now it's different. Now you have to do math. So in many senses, an operational amplifier is great. You know, you basically say, I have a device with a lot of gain. I put a few resistors around it and it fixes it to a specific gain. Okay, and I'm done. It's very nice from that point of view. It's very nice from dropping the distortion level or making the frequency wider, bandwidth wider. But it has a complexity. The complexity is this: a lot of devices inside, and each one of them contributes something. There's nothing free, right? So, yeah, okay. There are a lot of other devices, and we're not going to talk about them because there's just not enough time. So, real circuits. I think, yeah, okay. So, real circuits, we'll jump very quickly to devices that we use in real circuits. And the main ones today that I see people don't pay attention to too much, and we'll look in pictures later on inside equipment. The main ones are capacitors. Capacitors tend to come in all shapes and technologies. And you have the upper left Solon, 10 microfarad, very tiny. And then you have this one, 0.22 microfarad, 100 volts, huge. And you ask yourself, why? Because there's a quality difference, okay? You use metallized capacitor from Solon, you're gonna hear it. You use high quality capacitor from Duland, you're gonna hear that. Or Mundorf, you're gonna hear that. And there are things in between. There's the orange drops, the famous ones in the middle. And these two, for example, are used in AC filters. And I can tell you why I brought those into the picture, because I had a circuit that uses that. And I said one day, what's this Chinese capacitor like? I broke it and measured, and sure enough, there was a metallized foil. I measured the resistance and it was huge. It was like a few ohm over 1 inch. Then I took this one, I broke that, and you could go a few feet and you don't get 1 ohm. Okay, so there's a difference in quality. And this difference is very easy to spot because the more quality you put in, the bigger the capacitor becomes. Okay, either the thickness of the metallized foils or whatever, or if it's a foil versus just deposit some vapor, aluminum vapor, it's a lot thicker. Okay, so the big capacitors, and you'll see equipment with huge capacitors inside, to the point that it's almost not practical, like Connor Johnson. It's a big box with a lot of capacitors. There's a reason for it. Okay, now in some cases you can skip. You can use the lower level capacitors and bypass them. In supplies, for example, you can start with electrolytics. They're far away from the audio. If you have several stages in the supply, just make sure that when you got to the actual circuit that you have a bypass cap. That is good enough, like we mentioned before. All right, next. Noise. So every device has noise. If you look at the characteristics, this is a JFET, I believe. Yeah. So you'll see basically the device has, no, there's a op-amp. The device has a fixed noise for most of its bandwidth. And at low frequency, there's what we call 1/f noise. It's not really 1/f, but that's what it's called. And it's a phenomenon that's actually random, but it exists in many things in life in general, that at lower densities, there is more randomness. In this case, we think basically crystal structures behave differently and they give you more noise. So you'll see devices like JFET, look at the characteristic curves, how the noise is shaped. Some of them have very low 1/f noise, some of them don't. Generally, we're talking about noise density, and again, it's technology, but noise density, it's really the power of noise across the frequency bandwidth. And the more bandwidth you use, the more noise you're going to get out of your amplifier. In phono stages, we are dealing with audio. Okay, so the only thing that saves us a little bit is the RAA curve, because it cuts down. You have noise generated, but you cut it down with the curve, right? But still, you have to look at the device and see how much noise inherently the device has and how much low frequency noise it has. Okay, because remember, the low frequency RAA, we amplify the most, even though it's a very small range of the audio, but we have a lot of amplification for it. So you really want to cut it down. Unfortunately, physics is not working for us, so it's against us. So that's where we have most of the noise, unfortunately. But the hiss we're hearing from any amplifier is not only low frequency, it's high frequency as well, which tells you that all those curves, the power, noise power, are important. You need to look at those and you need to assess what device you want to use. If you're at the input stage of a phono stage, you have a lot of amplification ahead of you. Any noise there will be amplified a lot. You really want to use the best devices you got. That's why we see a lot of JFETs in there, okay? And when you go to tube amplifiers, you get more noise. They're inherently 12x7, inherently higher noise than a JFET for the same level of amplification. So it's not a fixed number. It's a fixed noise for a given amplification. If you get all your amplification in one device, one stage, you can tolerate more noise in that device. If you get
Input noise is the critical thing.
no, okay, versus, sorry, not more noise. You can tolerate more noise compared to for a single device of a lower amplification.
The noise on the output that you care about is referred to the noise at the
input. Yeah, that is true. That is true.
Okay.
Yeah, you still need to look at it. You're right. In most cases, what we do is actually multi-stage.
Yeah.
So if the first stage has a lot of amplification, it's the only stage
that matters.
That matters, right? And the rest of the stages are lower. If you have a first stage there's lower amplification, then you need to look at the second stage as well.
You need to redesign it.
Yeah. Well, not always. I mean, there are limits what you can do, right?
Yeah.
I mean, if you have a lot of amplification from a device, if it's very linear, that's fine. If it's not very linear, then you start to reduce that amplification, right? So you're playing the game, exactly. And there are other issues that we didn't touch on. I mean, there's, in addition to what I show here is voltage noise, there's also current noise. The higher current you run in a device, the more noise you're going to get. So you get the combination of the two, so you start adjusting. And these are issues that like RF engineers deal with every day, right? Because they deal with very low signals. Unfortunately, with Phono, we're dealing with exactly the same issues. Okay. So this is noise, the inherent noise of a device. So if you look at nanovolt per square hertz, it's the square root of the power, essentially. But the lower level is better. So you'll see all these JFETs or new op amps with 0.7 nanovolts per square hertz. I mean, this is a real good number. They're used in the front end circuit. In the later stages, you can tolerate other devices. Okay, noise and amplifiers. Okay, we don't have much time, so we're going to move on to power supply noise. So power supply noise, so this is a real preamp, John Uraga. And we're seeing the power supply rectification. So what he did is a lot of stages, right? I mean, there's basically a rectifier tube, and it goes into an inductor capacitor stage, and then you have 1, 2, 3, 4, 5, 6 stages of resistor capacitor. Okay, and the reason for that, I mean, then you ask, well, why should we have so many stages? Why not just put a big capacitor and the voltage will stay, as much, I mean, you're not consuming a lot of current, especially in Phono preamp. So just put a big capacitor and you're done, right? No. And this circuit shows, this picture shows why. Because if you put a big capacitor here, you're not going to get a lot of this swing, the voltage swing, or a hum level. Okay, so this guy, he put several levels of resistor capacitor. Each one of them knocks down the hum level. Okay, so in the end, he's left with 0.05 millivolts of hum, and you could have taken all those capacitors and lumped them into one capacitor here and got a similar level of hum. Why not do that? Why do it in stages? And here's the reason. So when we have a sine wave, okay, that we're rectifying, the sine wave changes from 0 volts to the peak voltage. Your capacitor bank in the power supply wants to maintain a certain voltage. Okay? If you hold this voltage fixed, that means it doesn't drop much. It stays there all the time. The diodes in the power supply don't conduct until they reach above that voltage of the capacitor bank. Okay? Then they switch into an on mode. And when the sine wave comes down below that voltage, the diodes switch off. So they're switches really. Okay. What's the time duration of conduction during the sine wave? If you don't allow a lot of swing in your first level capacitor, like here, 7.5 volts swing. If you don't allow that level of swing in percentage, then you end up basically then you end up basically with a capacitor bank that's almost at the top voltage, close to the peak of the sine wave in voltage, which means instead of conducting from this point to this point, it's now going to conduct from this point to this point. Okay? And when you think about, especially power amplifiers, I mean, they need a lot of power. If they conduct only in a very short duration, like 1% of the time, the peak current is going to be huge. It's not going to be the average supply current. Let's say that you need 10 amps to run the power circuit. Okay, this can be 100 amp if you cut down the time that the capacitor bank can actually be charged. Okay, if you allow more ripple, like higher swing down to the level of what the capacitors maintain, then you have a wider time frame that you can conduct. Okay, and you lower the current. High current, okay, peaks of current into circuits that contain magnetics are bad. Okay, don't do that. Or capacitors. You basically have noise generators. Okay, so anytime you switch the diode switch on and off, you get ringing. You get a lot of noise in that region. So there's a good reason to build complicated circuits for power supplies to lower the supply noise. And that's why we have AC cords that work better and those that work less, because all that noise goes out. Okay, and if you design the supply well, correctly, you reduce that noise. It's still there. You can tell. You can reduce it with other circuits, which is not here, but that noise is there, and you want to isolate it. That's why we talked in length about power conditioners and ferrites on power cords. If you have a supply like this particular preamp, you'll notice that your ferrite almost does nothing because there's nothing going on in noise from the supply. Okay, so we're getting into the real life effects that we've all seen. We just didn't understand why. Well, there you go. Okay, shunt regulators, we're going to talk about that. So a lot of times we will take a high ripple supply and run it through a regulator. A series regulator basically samples the output, brings it back to the input, a feedback circuit. Once it's a feedback circuit, if the output changes, like the current changes or the voltage changes, it's part of your audio path. It has to behave correctly and designed correctly for AC, for audio signals. It's not a DC device anymore. Okay, so power supplies in audio amplifiers and audio equipment are audio devices. They're not DC power devices only. Don't ignore them and say this is easy. Okay? The designer needs to know that. And there are a lot of designers that take it for granted. Like power supply, I'll just slap in some commercial power supply and I'm done. No. What are the characteristics of that supply? So you need to check that. The shunt supply regulator is a better regulator. Okay, you can take a high ripple power supply without all those capacitors. I mean, you could add those capacitors and have a shunt regulator. Okay, it'll be even better. But you could start with the high ripple and say, okay, well, how do I reduce it? You reduce it by saying, let's be independent as much as possible from the output, which is modulated by the audio. So we're putting a circuit in there. Those two transistors are current source. Okay, we can show that. they try to fix the current that goes through them. So this circuit consumes a fixed amount of current regardless of the output voltage. And then on the output, we're putting a Zener diode, which tries to stabilize the voltage over it, okay? Whatever current goes into it, it doesn't move in voltage, hardly, okay? And we can fix that in a way that we fix some current here that is higher than the current that your equipment needs. Let's say your amplifier, phono stage needs 30 milliamp. You can make this current source a 50 milliamp current source. This Zener will conduct all the time 20 milliamp. And if your circuit decides to, now I'm going to consume 5 milliamp less, it's going to go into the Zener, okay? In a sense, this circuit fixes by being a current source into a voltage stabilizer. It fixes the voltage on the output with no feedback. There's hardly any, there is some AC effect when you're consuming, when you're modulating the current on the output, but much lower than a series regulator, which everybody's doing. So a series regulator is cheap. You can go buy a three terminal silicon thing, easy to use. They work okay. Their frequency response behavior is not as clean as the shunt regulator. The shunt regulator consumes current. So you have a trade-off. Do you sacrifice current? So if you're building a power amplifier with hundreds of watts, no. Shunt is not a good idea, at least not on the output stages. If you're building preamps, phono stages, sure. And when you sacrifice half a watt, you get a much cleaner supply that's independent of the audio. So shunt regulators all the way. And now we're getting into the actual building blocks of a phono stage. So in general, we will see the following. We'll see an input stage where first we need to load the cartridge, as we talked in the beginning. Then we need a low noise input stage because we know the gain is huge. At least the gain of that stage should, the noise of that stage should be very low. Once you pass that stage, you can allow a little bit more noise because it doesn't, it's not amplified as much. So we get to this point with the first level. I'm just giving an example of the one unit that we have, but a lot of units follow the same concept. So you get a gain from 5 millivolts up to 100 millivolts, a gain of 20, sort of. Then you use active or passive RAAA network. You may have a low pass on this circuit in the beginning and several other stages that form all the RAAA. Or you may have just a resistor capacitor network that forms the RAAA response and what we call passive RAAA. So we have a stage as an amplifier. It goes into a filter with resistors and capacitors. And what comes out here is corrected levels. So the bass through that network comes out higher level than the treble. And from that point on, we're just amplifying. This is a phono. This is not phono anymore. This is now amplifiers or a preamp. So maybe one stage, maybe two stages. And then we have the issue of going out into the real world load. Some of them buffer more. Some, especially tubes, they'll put like a cathode follower circuit. It's a circuit that lowers the output capacity, output resistance, so you can drive more cable. Okay, so each one of those circuits has its own characteristics. Low noise in the beginning, high drive on the output, frequency response in the middle. Okay, and simultaneously with that, I'm showing the power supply chain. So power supply starts with the rectifiers, capacitor bank, which we talked about, and then maybe the input stage needs a better quality supply because it's amplified. Any noise in that, including the supply, will be amplified more. So maybe a special regulator for the input stage and other regulators for the rest of the circuit. In some cases, a single regulator is good for everything. Okay. So it looks like we're going to go well over the time. So we'll go very quickly through the examples. So passive and active RAA, I'm showing just an amplifier, an op amp. It doesn't have to be an op amp. Okay, it can be a transistor. So some of them have an amplifier. The active basically puts all the resistor capacitor of the RAA in the feedback of the amplifier. The passive says, no, let's just amplify and then put the resistor capacitor. And the hybrid will put some of it in the feedback, some of it passive.
Do you have a personal feeling about which is better?
Personally, I like the passive. I think it's easier to design amplifier stages. I mean, in some cases, I will tolerate like a hybrid where you have like a simple, like a low pass in one in the first stage. You cut down the noise that way a little bit. That's acceptable.
All of your circuits there are inverting.
So
That means the input impedance is low. The normal Phono preamp, you want a higher input impedance, you go on the plus input.
okay, this is again not necessarily.
No, too many applications where people go in the negative input.
No, not necessarily. Why? I mean, yeah, I mean, I understand what
The
you're saying.
real issue like driving the input circuit because that gets caught up.
Yeah, but a lot of times you don't have that problem. I mean, you have 47K, you're fine, right? I mean,
47K series resistor, the noise floor becomes that of the resistor.
no,
Yes.
no. That's what most people think. 47K is the problem. The 47K is there if you don't have a cartridge.
No, if you come through that resistor to the input
Yeah,
of the
if you come
circuit
through that, yeah, that's.
and an inverting circuit,
But you don't need that, right? I mean,
but that defines if you're going to the input.
Yeah.
Because the inverting input of the amplifier there is a 0 ohm impedance.
there,
And the circuits you've drawn there, yeah.
That's just an example though. right?
yeah, I mean,
Yeah, you just sort of swap that around, ground the input.
I mean, you know, yeah.
The input to the plus.
yeah, I mean, usually I don't put, I don't use op amps, so I just took some circuits. But you're right. I mean, you can make the.
Yeah.
You're right. You can make that the positive input non-inverting, and yeah. Usually you'll use in the input stage at least. You'll use like a JFET, which is essentially high impedance, so you don't have that problem. Correct. Well, maybe I'll change that. If we, yeah, there you go. But it's an easier example, right? I mean, I don't want to put transistors with the whole circuit in there, so an op amp is easy. So just to explain, but the concept is basically an amplifier with a feedback, whether you put the
feedback at the negative cannot be in the positive, right?
no. Okay, let's not get no. An op amp can be either. Okay, so but you have an amplifying circuit, and you put a feedback around it with a frequency response. That's an active filter. Okay, if you put the frequency shaping components after that stage, okay, like we're showing here, that's a passive. Okay, it just the load is shaping the frequency response, and you can come up with a scheme where you're using both. Some of the frequency response is shaped in the feedback, and some of it is a passive component. So that's the first part, and it took the whole session. So I'm sure there are a lot of questions, but yeah. I think what we could do is like 5-minute break and come back, and I'll go through examples very quickly because we just don't have time. And if somebody wants to have lunch, maybe we should order. What do you think?
Sure.
Subway? Actual design. So we're gonna go through very quickly through a few designs, and we'll try and make it in like 20 minutes maybe. So we're starting with a very, very simple unit. It looks like this. Okay, so we have 2 operational amplifiers. These are 2 channels, so each one of those is a dual op amp, and that forms 2 amplification stages. And you see loading here, some resistors, you can change the loading. You see gain, you can change some to some extent. And you see those capacitor, the RAAA circuit. So let's see what the circuit looks like. They actually advertise the circuit. So this is the circuit. The loading, obviously here, and then you have, you're right, a stage, an amplification stage, and then you have a passive RAAA, and that goes into the second stage. This is a change of a resistor to change the gain. Okay, the gain is basically this resistor divided by this resistor plus 1. So by changing this resistor, you change the gain. So this is the simplest ever form of a Phono stage, okay? And it's available for $30, something like that.
Mm-hmm.
The only AC coupling is at the output.
Only at the output.
So with that much gain in those devices, you could end up with a volt on you stuck in that cap.
Yeah, I don't know. Well, that's why you have a gain control, right?
That's 5 millivolts offset at the input there.
Yeah, that's true. It's not ideal, okay, but it's in sockets, right? So you can change. Yeah, you can change the op amps. This is it started as a DIY on some forum project, and then ended up with whatever. So this is LT1115, a very low noise bipolar op amp. Okay, and it's one of the first low noise designs. So this is an op amp. This is a circuit that was put together by a guy that actually used it. The application engineer at Linear Technology. And he biased the amplifiers. As good as this and expensive this amplifier was, it's not class A on the output. So by putting a current source here, you bias it into a class A. It's a current source load, essentially. And because it's low level, it's good. You don't need a lot of drive, so this is good. And then he buffers it with the device, Linear Technology device. The feedback has the RAAA in it, and life is good. Okay, this is real life design optimized by an application engineer that knows what's inside the op amp. Okay, so if you're gonna do any DIY project, it's a good one to start. Parasound, John Curl. So this is not the real circuit. This is somebody put together a circuit. I'm sure it has errors. So, and it's incomplete. So basically, op amp back to back, several stages. This is an MC. So basically, has very low offset, very low noise input device. Actually, in today's standards, I'm not sure, but
It's
at least and then two levels of amplification there. You'll notice the same trick as the linear technology. All the stages are biased into class A by putting some transistor, which is a current source, okay? Current source essentially takes a push-pull circuit and forces it to conduct in one direction. So it sort of turns it into a single-ended circuit with a high impedance load. A lot of technology, but it does linearize the circuit a tiny little bit. So, but what we see here is building blocks are similar. I mean, essentially we have an amplifier with current source, some shaping, frequency shaping here, passive, an amplifier with some frequency shaping, active, and an output stage. In this case, there's no output capacitor because the output is sampled, goes into a DC servo, which we'll not talk about, and it returns into somewhere in there to cancel. So essentially you're taking DC, you're sampling the output, you're saying how much DC is on it, return a correction to move that DC to 0. Okay, and you avoid putting a capacitor on the output. So if we looked at the 2 slides before, there's a capacitor right there on the output, and this capacitor is not negligible because it's driving a preamp. Okay, so it has to be a large capacitor, and large capacitors, high quality large capacitors, are expensive. So we'll see another example of that. So there's the parasound. The next one is very, very similar. This is a famous analog designer from the 80s. Very similar design. Again, we have amplifier, RAA amplifier. Okay, and in this case, he opted to simplify, so he went with a 10 microfarad capacitor. 10 microfarad, I guarantee you, he's using electrolytic. That compromises the sound quality. So it's all a compromise. Now we're looking at the real designs. This is Mani 2. Mani 2 is also an op-amp based design. So we're seeing those op-amps. We're coming in from that side. These switches are the loading switches, essentially for the resistors, and they're on the other side. Goes into this stage. You're looking, where's the RAA? Yeah, those little tiny devices over there. Well, how much quality you're going to get from tiny capacitors of this size? Okay. So next thing, you go through a second level. Probably, I mean, I don't know the circuit, but probably very similar to the 2 op-amp circuits that we looked at before. Output, okay, not great. Now, all this area is regulation. The nice thing about it, we'll look at the next one later. The nice thing about this design is that there's no switch mode power supply inside. It's actually a linear power supply. It starts with a 16 volt AC, generates internally 10 volts, split that internally into plus minus 5 volts. It's all linear. So it's taking advantage of op-amps that are working at plus minus 5 volts. That's newer generation op-amps. Not necessarily the best approach. Okay, there's a when a manufacturer puts a focus on low voltage, usually they drop something else. Okay, so it could be noise level or something. Okay, but it's okay for what it is. $129, I believe. And
It's a nice little photo stage.
At this price level, the manufacturers are trying to avoid liability, so they're not going to build AC power supplies. They're going to use wallworts that they can buy for $2. The liability is on the manufacturer, right? And their device is fine. They don't need to certify anything. However, this is a compromise. So you can get 16-volt AC. Now you're limited to low voltages. Unless you're iFi Zen, and then you start with low voltage AC, but you want more. Well, what do you do with more? Or in this case, they're actually starting with the cheapest supply they can buy, a 5-volt standard USB kind of charger, right? So they cut down the price and ended up with no liability. Now they need higher voltage because they made a decision to use very new, very low noise, very low offset op amps. So the solution is a switch mode power supply running at 1.2 megahertz. They claim that because of the high frequency, it's very low, easy to filter, so very little noise goes into the circuit. However, the company that owns iFi is AMR. AMR has a few Phono stages. They don't use switch mode power supplies. Tells you something about it. They cost also a lot more. So these are examples of op amps, different varieties, different compromises. Okay, we will listen to the iFi Zen. It's supposed to be extremely low noise devices. And the other thing that is interesting about it is in this area, you'll see a lot of components. This is the RIAA. So instead of using big capacitors, like very few, we saw, you don't need that many. They use many little capacitors in parallel, and they use very specific ones from TDK. They claim that the quality and the tolerances of TDK are much better than the average. Therefore, they can be more precise. Okay, it's a question, so you'll listen to it, but at least that's the claim. And
Is the iFi Zen?
it's like $200 today. It started at $150. So we'll listen to it. It's quite credible. Let's see. A peek inside the Sutherland 2020. So Sutherland says, let me give you the best supply possible. So one solution that he came up with was batteries. I think C cells batteries.
Yeah,
Yeah.
a bunch of them.
Yeah, and then he came up with this and claimed that this is actually lower noise. And the way you make it lower noise is you start at 48 volts. And you drop it down because you have 11 stages of RC. And we looked at that RC, the tube guy, right? That put a lot of, well, this is the same concept. And the cost of doing extremely high rectification or stabilization is you're paying with voltage because you're going through resistors. And each one of them drops a little bit of the supply voltage. So you start with 48, you end up, I believe, with 24 volts. So you're dropping essentially half your power on this circuit. So you have this big box. It has all this for power supply, this for the Phono, this for the RIAA. You look at those half decent capacitors, not the best, but somewhat okay, and the loading in this region. Okay, in essence, op amp, preamp, Phono stage. Okay, done well, with very high quality or attention to the supply. Not very high quality RIAA. Okay, but that's typical. You're not going to find extremely high quality capacitors until you get into.
So, sorry, how much is this one?
This one's like 2000, I believe.
Yeah,
Mhm.
I used to have one.
I think.
I don't see how he uses.
I mean, but you could essentially take another op amp, decent op amp based phono, put batteries on it, and probably end up with similar results because the circuit is not outrageously different. I mean, once you start with op amps, you're limited to certain topologies. There's no funny stuff there. And in fact, I would say the JC2, which uses discrete devices to bias the op amps, is a better design. And I think it sells for about the same. Now we're jumping. Boulder 2008. So we're looking inside.
It has the most yellow parts.
Yeah. Well, the yellow is actually different here. So yellow parts here are not capacitors, they're actually relays.
Mhm.
So it's a very flexible design. You can adjust a lot of things, right? And instead of adjusting them with switches like the other cheap ones are doing, these guys have buttons and they apply it to relays inside. The nice thing about this is that the change happens near the circuit. So the audio path is very short. That's nice, of course. The bad thing about it is that you have some digital noise from push buttons kind of a thing. So I don't know how they implemented that. I mean, it could be digital. So let's see, how much supply regulation? Not that much. And most of the design, I mean, these are op amp blocks. You remember we talked about the discrete op amps, the D990 and Boulder redesigned it. This is the 993. It's essentially a super duper discrete op amp, the Jensen 990. And then they created one more low noise discrete op amp, one that is very special because they want the front end of the whole system to be lower noise. So this is at the 995. And that's typical to Boulder. I mean, that's what they do in all their phono stages. There's always a lower noise first stage and the standard op amp, discrete op amp following that. Now, in essence, each one of those op amps, functionally, okay, I'm not saying quality, but functionally is the same as these op amps, okay? Or maybe that's better. Or maybe this one, like John's. So this can be a 995, 993, 993. The circuits are not much different because the discrete op amp, in essence, is an op amp, operational amplifier, has negative, positive inputs, has output, and it has some compensation, which some discrete monolithic op amps will also have. So the difference is that the density of tiny op amps that you're buying, you know, with 8 pins is much higher than the modules, the 993 or 995 modules that Boulder puts together. The function of the circuit is about the same. It's an operational amplifier. So what we're seeing here is essentially a slightly more flexible implementation. So Boulder basically has several inputs. Each one of them has a card. You can see the blue thing, that's a socket. So you customize the loading by plugging in a small board that has resistor and capacitor on it. And it has other things that control the gain, but in essence, the resistance, the loading is something you buy for your particular cartridge. and this is a good way of doing it instead of switches. Switches can be problematic. The contacts corrode or whatever. So this is a safer way of doing it, let's say. And then you go into your head amp, the first stage. And for some reason, they have 3 stages following that. I believe the last stage is just the balance to invert phase. And I think we'll show another one that does that. But all these yellow things are relays that control the characteristics of the particular circuit. The RIAA is implemented in plug-in cards. So there's a card here, a card here, a card there. You can have several curves and you can select between them. So you can have a Columbia curve, London curve, and standard RIAA. Those relays will click when you select one of those. Okay? However, this little card, when we're talking about little card, surface mount devices. Think about the capacitors that you're putting on that card. Are they the highest quality possible? Maybe. So there are compromises when you're dealing with that. There are nice things in the design. There are some things that are compromised, even in a $25,000 or $29,000 model. This is the 1008. 1008 is a lower version of the 2008. So the 1008 still has the loading cards. You can see the blue things in there.
When you say lower version, you mean less expensive?
Less expensive.
Thank you.
And you can tell, we'll show in a second. So basically 985 is their lower cost version of the 995. How much can you save? I'm not sure, because it's still a discrete op amp. So this looks actually fairly decent for an input stage. However, there got to be some cost cutting. So there you go. This is the 993. Okay, it's a plaque. It's essentially just some circuit. Is no different than other discrete circuits. So there's no special module here. It's just a plaque. And what you'll see is op amps. Those are controlling the low cut. I think one of them is very specific. Yeah, the low cut is right there. And pretty much the output. So they basically customize the input with the 985, and they cut down the cost on the output. Okay, so this is just surface mount, which is the cheapest to manufacture. Versus if you look at the 2008, it is surface mount some, but not a whole lot. I mean, the center, which is probably also digital, surface mount. But the op amps and relays, they have to be inserted by hand and soldered, so there's cost to it. So it's attention to detail. And this is the RIAA board, which is vertical in the 1008. And you can actually customize it. So, but customized by selecting different relays. Unlike the 2008 where you had 3 slots and you select between the slots. However, look at those devices. I would say between the boards that you plug in the 2008, $30,000 device, Phono stage with tiny capacitors. This one has real world, decent sized capacitors, some quality in the RIAA that actually exceeds what I think exceeds what they put in the 2008. And those are design compromises. You make a box and then you're limited to whatever you can plug into that box. Maybe the space doesn't allow you to do certain things, or you think this is good enough. You know you can do better because I'm sure they tried with big boards with big capacitors, but it didn't fit the model. So there you go. You compromise on something, even at $30,000. This is the stellar. We're gonna actually listen to it. Thanks for bringing this. I was really looking forward.
I could have brought my Boulder 1008 too, if you wanted.
Yeah, I mean, we're limited on
No, I know.
how much you can go, yeah. So basically the stellar concept was, I'm gonna build an op-amp, discrete op-amp rather than op-amps. And I'm gonna make the op-amps as linear as possible. And this guy worked really hard on this, and it's ended up with big circuits with a lot of devices. I mean, the whole thing together, 720 devices. Okay, that's a lot of stuff. But if you're looking at it, you'll see structures. You see this structure is similar to this structure. This is similar to that. This is similar to that. So these are discrete op-amps. Okay, they're built from little transistors. They're surface mount. Not much different than like this. Or, well, I mean, the Boulder 1008 has a few op-amps in here, real op-amps that it's using, but I believe it has some transistors under there. So that's somewhat discrete. This guy says, no, I'm gonna go full-blown discrete. Okay, and linearize each one of them as much as possible. There are a few YouTube clips that the designer Darren Meyer is talking about. It's interesting to listen to the process, how it went about. Now,
Discrete means it's made of individual parts.
individual
Specialized.
resistors,
All right, specialized. op-amp.
yeah. Versus, I mean,
Versus an off the assembly.
an op-amp is just, they took all these devices, put them on
Yeah,
one piece of silicon.
Right,
You don't have a choice. Here you have a choice.
right.
So let's look at what's in it. With all those 720 devices, there's still a lot of devices in the active circuit, but look how much goes into the power supply. All this area is power supply. Everything here. This is regulation. So a lot of the quality of Phono stage is in your power supply. I mean, you looked at all these examples. If they're serious, they have decent power supplies. Okay, because that's a lot of noise can come from that. Not only hum. And then you have a standard circuit. You have the moving coil input stage, super low noise. And then you have the standard phono, moving magnet phono stage, the two-stage design. And you have an RAAA with reasonable size capacitors, okay? I would say the quality of capacitors in the RAAA here exceeds the Boulder 2008. So I think the guy basically designed, you don't think?
No, I'm asking, does this sound better than the 2008?
I don't know. We'll listen to it. We'll listen to it. We don't have the 2008. We cannot tell.
We had at Don Naples last year. Last year we had a Phono stage shootout. We
Yeah.
had the Stellar and we had my 1008.
1000, yeah.
We had an issue with the Stellar. There's selectable gain and loading. And then there was a variable.
For the moving coil, yeah.
Yeah, and Don had engaged the variable one and
Didn't know how to set it.
not do well at all.
Oh, really?
And when he sent it back to PS Audio, they checked it out. They said it was fine. Sent it back, and somehow he just turned off that variable pot and used just the selector switch, and it was a huge difference.
Really? So there's something wrong with the, okay, we won't use that.
Well, yeah, so don't use
Not
that,
moving
but
close.
so what bottom line is what we heard at his house wasn't really representative of how good it could be.
Yeah.
Yeah.
That's really unfortunate.
Has he listened to it in the system since then?
Yeah,
So-
oh yeah, yeah, he said it's much better. He did end up, I think, with a Pass Labs Phono stage. But he's keeping this one for a second.
Yeah, for a second system, you said.
Hey, Ori, are
Yeah.
you gonna try to get to lunch and get back?
Yeah, let's go through two more, I think. So this is a discrete amplifiers, passive RAA amplifier, and it's a JFET. Okay, this is, I believe, a $30 eBay. However, look at the quality of capacitors. Decent, half decent. This is Darlington Labs. Discrete, all discrete. Quality of capacitors, so-so. Okay, and I think Jim listened to it. This is what not to do. This is a Class A DR6 preamp with a phono stage. There are 1, 2, 3, 4, 5, 6, 7, 8 stages of transistors. Essentially, this is the safe design. One circuit, one amplifier, buffer, one amplifier, buffer, one amplifier, buffer, and one amplifier, buffer. Don't do that. If you're designing even DIY, don't do that. There are 5 electrolytic capacitors in the path. Don't do that. The funny thing is, I heard it. Sounds good. What can I say? This is the phono stage from Past Labs, from Dynaco, Past Labs, Dynaco. So just amplification stages. The feedback has the from output to input, RAA. Standard circuit. Everybody in the 50s copied it. So in one version or another. Cornet is very similar to EAR 834, except for it's a passive RAA. So we'll listen to the cornet. It basically has an amplification stage, passive RAA, amplification stage, another passive RAA, like split the RAA, and then an output stage, which is a buffer. So it's really two gain stages and a buffer stage, and capacitor output. There's a nice circuit here. I don't have it in the unit here. A mute circuit, but that's about it. To my unit, I added the Zeners and changed the resistors a little bit, so it has a little bit better regulation, but it's not a massive change. I believe the new version, because of again liability, you moved to a different power supply. This is a tube power supply. The new version is a solid state switch mode power supply. I don't know.
What do you mean by liability? What liability?
Liability is when you sell something with that connects to the AC. You have to certify that, and if somebody gets electrocuted, they'll check.
Legal liability is what you're talking about.
So essentially, the new one I believe is like a 12-volt core module, and then a switch mode power supply generating 150 volts internal. I guess that's the new direction for low cost devices. So you can still buy that. I don't know what it sounds like with the switch mode, but we'll listen to it because it's a pretty decent circuit. The EAR 834 is very, very similar, 3 stages with a feedback RAA, not passive. Between the two, the price difference is like double. So this one will be like $700. The other one is $1,500. And I think I would probably prefer this, but it's a maybe. This is what's inside, so you can see decent capacitors. I mean, I opened it up to replace the RAA capacitors. I looked at it, I closed the box. It's fine. All those white capacitors.
Multi-caps,
Yeah, they're multi-cap.
hard to improve.
Yeah, so it's good enough. And this is not a very high cost unit. This is the EAR 834, like similar circuit, just a feedback. RAA is in the feedback path. Luxman, which we're going to listen to, similar concept, a lot more power supply in the Luxman. The Luxman also adds a transformer on the output, which is interesting. And for moving coil, it uses transformers on the input.
So does the EAR.
The ER has a transformer out?
Yeah.
Out?
Well, no, input.
On the input, on the MC, on the moving coil,
This
yes.
is also an SRPP circuit, it's not the same,
And it is SRPP circuit, yeah.
it's not the same.
Yeah, but I mean, very similar concept, yeah. And we're gonna listen to that. Yeah, in a sense, I'm not sure I like the SRPP, but anyway. This is static REA, static IO. Look at the capacitors in there. The orange ones, they're pretty massive. So that's where they put the money. And this is the power supply chassis of the static REA, which has tube regulators. So there's attention to detail, and it's in the supply, not necessarily in the audio circuit itself. Bellari, forget it. This is the Pearl 2. So this is the one that Jim built. Essentially, it started from that. So this is op amps, JFETs, and you put them in parallel. You get more gain for less noise. Okay, the more of those you put in parallel, the better signal to noise you're getting. To some extent, so 4 to 8 is pretty standard. The circuit here is just to clamp voltage. We're not going to go over it. So RAA is passive, and then we have a circuit here that is really plus input, minus input, and output stage coming back. It's an op-amp circuit. It's a discrete op-amp for those who can read the schematic. So basically a JFET input, passive RAA, discrete op-amp output. Very decent circuit design by a good design. I mean, 30-year designer of Phono stages. So I think we'll listen to it. We did some things to improve. So when we look at it, there's a capacitor here, 22 microfarad electrolytic. Okay, I don't like that. So we put DC servo around it. These are series regulators. We talked about them. We changed them to shunt regulators. What was the total investment? $35?
In regulars, like.
Yeah. Yeah. And if you eliminate this, you save. So it's like $30.
And
So
the improvements was monumental, or?
Yeah, we did everything in stages, so it was nice. And it helped.
yeah, and of course all the capacitors changed. So we'll show a few of those. So these are the changes. Servo circuit. These were gone. Well, shunt regulators added, and capacitors changed. That's about it. But it was a major difference. So this is a circuit board of the final design. So you can see all the original regulators were taken out. So it's half the board essentially. These are big capacitors. You can see they were designed for those tiny WIMA capacitors. Okay. Instead, these are metal foil capacitors. Big difference. And this is the servo which Jim built on a separate board. And now you would say, well, he does have a WIMA in there. Yes, but this is really not in the audio path, okay? Because there's a big cutoff at 0.5 hertz for that circuit, okay? So you're not gonna hear that. But when you put a DC servo in the output circuit, you're stiffening to some extent your bass. There's an effect on the bass response or the bass quality. This is XP15. And yeah, no time to go over it, but essentially it's discrete implementation. So-so on parts quality. Supply is on the same board as the main unit. So there are compromises, and this is what, $4,000, something like that. This is the top of the line, $45,000, okay? So you would think this is it, you cannot improve. Well, no. This is the input circuit. I'm not sure exactly. Discrete transistors. No shielding around it or anything like that. At $45,000, I expect that. I mean, Boulder at least puts everything in a metal case, okay. RAA is okay, not stellar. Parts, you would expect better parts at this price range. I'm not sure what this is, but that looks like a commercial part in the power supply. There are regulators here, there's digital here. So then you ask the question, I mean, how much is this an improvement over the XP17 that we saw before? Price difference is like 10x.
Wow.
So there are definitely compromises in any design, but the question is to what extent you're accepting the compromises. There's a power supply chassis to this, so to some extent, power should move down. What? No, this was a demo unit that was in a show. So this is it. I think we learned hopefully quite a bit, and we have some idea what's inside. And always remember, history repeats itself. You know the picture of the guy, you know, the Microsoft thing that starts leaning at the end. Same thing, I noticed that with audio. So we're starting with nylon. You remember those from the 70s? With nylon and little metal, and then somebody said, no, we need more metal. Oh no, we need more metal, and we ended up with a Boccino, which is like a hefty thing, like a quarter pound. And then this is Australia. And then another guy from Australia said, no, there's too much metal. Let's go back to nylon. So we ended up returning to this, except for we're paying a lot more for it. With the tube amps, we're looking at 45s. We improved because we want more power, 283, 807. Then somebody said 6L6 is better. Let's make it ultra linear. We ended up with 1250 watts. And then we're back to a refined 45 amplifier. So
As God intended.
yeah. So history repeats itself. So what's next for Phono? There you go. All right, we reached the end, an hour late. So we can go grab something quickly to eat, and I think we'll delay the next session probably half an hour. What do you think? Okay, so the system in the next session is basically this.